Pyridine. It is also called azine. The molecular formula is C5H5N and it is represented by this structure, and numbering is done from nitrogen 1, 2, 3, 4, 5 and 6. If we give numbering alpha position or beta position, these are represented as these two positions are alpha, these two positions are beta, and this one is a gamma position. So pyridine is a very important 6-membered heterocyclic compound. This pyridine ring system is present in a number of natural products such as vitamins like nicotinic acid and pyridoxine, and it is also present in most of the alkaloids like nicotine and piperine. Resonance structure. Pyridine is considered to be a resonance hybrid of the following structure, which is represented by this. As you know that nitrogen is more electronegative than carbon, so it attracts the electron density toward itself. So nitrogen has one lone pair of electron, and this electron density is attracted toward nitrogen. And in the next resonating structure, this carbon acquires the positive charge. And this electron density is shifted here. See this. In the next structure, this electron density is shifted here. So this nitrogen acquiring these two pair of electron and this carbon acquiring the positive charge. So this means the electron density is less at position number 2 and 4. So resonance hybrid structure not only explain the stability of pyridine ring but also supported by its bond length. Carbon-carbon bond length here is 139 picometer, which is in between carbon-carbon. Double bond length is 134 and carbon-carbon single bond length is 154. So this is very near to double bond length. Here carbon-nitrogen bond length is 137 picometer. So it is also very near to the double bond length. And this pyridine also shows dipole moment. So that shows it is a polar molecule. So what will be the molecular orbital picture? Here carbon is sp2 hybridized. So this one is, as you know, 2p orbital containing single electron. So it is sp2 hybridization. So nitrogen is again sp2 hybridized, and one of the hybridized orbital contain lone pair of electron. So this condition is different from that of pyrrole. So each hybridized carbon forms 3 sigma bond, 2 with carbon and one with hydrogen. See this. So each carbon forming 3 bonds. So we having carbon-carbon bonds, carbon-hydrogen bond and carbon-nitrogen bond. And each carbon and nitrogen is having one unhybridized orbital which contains single electron. So this hybridized orbital of nitrogen contain one lone pair of electron, so which is responsible for its basic character. So the unhybridized orbitals overlaps as we have a delocalization. So that is confirmed from the double bond length. So this is the molecular orbitals picture of pyridine. So pyridine is a very colorless hygroscopic liquid which is boiling point 388 Kelvin. So it is a very unpleasant smell, but it is a very good solvent for most of the organic compound. So pyridine, because it has lone pair of electron, so it is behaving as a base. See its basic nature. So when pyridine is treated with HCl, so we have this pyridinium, the pyridine chloride salt. So when it is treated with methyl iodide, so I am getting pyridine, methioiodide. But pyridine is a weaker base than aliphatic tertiary amine. In case of pyridine, nitrogen is sp2 hybridized, whereas in case of aliphatic tertiary amine, nitrogen is sp3 hybridized. So sp2 hybridized nitrogen attracts the electron more closely to itself. So it is not available for donation, where it is less electronegative and it can easily donate the electron pair. So it is a strong base than pyridine. But pyridine is a stronger base than pyrrole, because in case of pyrrole, the lone pair of electron is not present. It is used in the delocalization of the pi electron cloud. So let's explain the electrophilic substitution reactions. So pyridine is very less reactive than benzene towards the electrophilic substitution, because nitrogen is more electronegative than carbon. So it attracts the delocalized pi electron cloud towards itself. So carbon atom of the ring have the lesser electron density. So electrophiles can't easily attack the ring. Another condition is that the most of the electrophilic substitution reactions such as sulfonation, nitration that takes place in the acidic conditions, and the nitrogen atom of the pyridine gets protonated. So the electrophilic substitution reactions takes place at position number 3, which is you have seen in the resonating structure, because it is the position where the electron density is more. So let's do the electrophilic substitution. So pyridine, when nitration is done in the presence of potassium nitrate and sulfuric acid. So the nitro group will be introduced at position number 3. 1, 2, 3. 3 nitropyridine. Sulfonation is done in the presence of sulfuric acid at 623 Kelvin, and the sulfonic group will be introduced at position number 3. So we get pyridine 3 sulfonic acid. But when we do the bromination, we get 2 types of product. 3 bromopyridine and 3 and 5 dibromopyridine. As pyridine is less reactive, so acylation and alkylation that do not take place. No reactions. So let's do the mechanism and orientation of electrophilic substitution reactions of pyridine. As you know, the mechanism has 3 steps. The first step is formation of electrophile. Second step is formation of carbocation. So let's explain it. So we take the pyridine, and the electrophile will attack at the position 3. Which one? 3. 1, 2 and 3. So this electron density is shifted to this carbon. This bond is here, this bond is here. Because electron density is shifted from this carbon, so it requires the positive charge. Again, this electron density is shifted here. So we get the bond here, and this acquires the positive charge. So now this electron density is shifted here, and we get the positive charge here. And this step is a slow step. So this is a rate determining step. So third step is loss of proton. So कोई भी न्यूक्लियोफाइल ਕੀ ਕਰੇਗਾ, ਇਹਦੇ ਵਿੱਚੋਂ proton ਕੱਢ ਕੇ ਲੈ ਜਾਏਗਾ, and the electron density is given to this carbon. So we get this 3 substituted product. So now we discuss the orientation of substitution. Why not the attacks takes place at position number 2 and position number 4? So let's write the structures. So the electrophile is attacked on this position number 2. So when this is shifted here, this carbon acquires a positive charge. But this structure is unstable because nitrogen, being electronegative, acquire the positive charge. So according to the resonating condition, when the electronegative atom acquires the positive charge, that is the unstable structure. So now the electrophiles attacks at position number 4. So we will write the resonating structure. Again, this electron density is shifted here. So this is again unstable structure. So when the attack of electrophile is at position number 2 and 4, one of the resonating structure is unstable. But when it attacks at position number 3, no such structure is present. So the electrophiles attacks at position number 3. So let's explain the nucleophilic substitution reactions in pyridine. So you have studied the electron withdrawing effect of nitrogen atom. So electron density is decreased. So at position number 2 and 4. So we'll write the resonating structure. So electron density is decreased at position number 2 and 4. So let's take some examples of nucleophilic substitution reactions. So pyridine, when treated with QOH at 573, followed by hydrolysis, so we get 2-pyridol. So that undergoes tautomerism to form 2-pyridone. Similarly, so when it is treated with phenyl lithium, the phenyl group that will be introduced at position number 2. So we get 2-phenyl pyridine. So when it is treated with butyl lithium at 383, the butyl group will be introduced at position number 2. So we get 2N-butyl pyridine. So let's discuss the mechanism and orientation of nucleophilic substitution reactions in pyridine. So nucleophilic substitution reactions in pyridine takes place at position 2 and 4. It has the following steps. So let's take example, this pyridine when treated with sodamide at 375 Kelvin in the presence of toluene solvent, we get 2-aminopyridine. So let's write its structure, how the attack takes place. In the first step, the amide that will attack, and we have this type of structure. So this lone pair of electron is shifted here and this is shifted here. When shifted here, so the carbanion formation takes place. This bond is here. This bond is shifted here. So the resonance stabilized carbanion takes place. And this structure is stable because the nitrogen is being electronegative, acquired the negative charge. And in the second step, the resonance stabilized carbanion loses the hydride ion. And this step is a slow step, fast step, sorry. And this is not a rate determining step. And rate determining step की है carbanion formation. Now we will discuss orientation of substitution. So why the attacks also takes place at 4 position, and why not the attack takes place at position number 3. So we will write the again resonating structure. So when the attack takes place at position number 4, the nucleophile attack this. So when the attacks takes place at position number 4, again we have the structure this one, which is a more stable because the nitrogen acquires the negative charge. But when the nucleophile attacks at position number 3, no such structure is there. So nucleophilic substitution reactions takes place at position number 2 and 4. So let's explain the reduction. So reduction is depends upon the reagent we are using. In case of hydrogen and nickel at 473 in the presence of sodium and ethanol, so we get pyridine. When we would do the Bsc reduction, that is sodium in the presence of ammonia and ethanol, so we get 1,4-dihydropyridine. And when we do the lithium aluminum hydride followed by hydrolysis, we get 1,2-dihydropyridine. And when the reduction is done with hydrogen iodide in the presence of red phosphorus, in pyridine we have this 5 carbon, we get pentane and ammonia. So the nucleophilic substitution reaction takes place at position number 2 and 4. And the lactophilic substitution reaction takes place at position number 3. So let's do the oxidation. So pyridine, like tertiary amine, is oxidized with per acid. And we get in the presence of perbenzoic acid, so we get pyridine N oxide and benzoic acid. So let's compare the basicity of piperidine, pyridine and pyrrole. Pyrrole is less basic than pyridine. Pyridine is less basic than piperidine because in case of pyrrole, the nitrogen is sp2 hybridized. In case of pyridine, it is again sp2 hybridized. Electronegativity is same. But in case of pyrrole, the lone pair of electrons are not available because they are used in the delocalization of the pi electron cloud, wherein in case of pyridine, the nitrogen is having the lone pair of electron. So when we compare the pyridine and pipyridine, in case of pipyridine, nitrogen is sp3 hybridized, as nitrogen in case of pyridine is sp2 hybridized, it is more electronegative. More. So, it closely holds the electrons. So, it is not available. But in case of pipyridine, nitrogen is less electronegative. So, it loosely holds the electron. So, it can be easily available for donation. So, pipyridine is more basic than pyridine. That's it.